Hey guys, by this time you already know what are exponential functions. In this lesson, we would understand the difference between exponential and logarithmic functions. An exponential function looks like y equal to 2 to the power x. So the general equation is y is equal to b is any base. This base could vary to the power x. Whereas a logarithmic function looks like log to the base of b of x is y. So always remember, a logarithmic function is an inverse of exponential function, and we all know how to find out the inverse of a function. So if I want to find out the inverse of y equal to 2 to the power x, all I would have to do is just interchange x and y. That gives me x equal to 2 to the power y, and then solve for y. If we have to solve for y, we have to change this to logarithmic form. And how do we change it to logarithmic form is, we write down the base b as 2, because the base of exponential function is 2, so the base of logarithmic function stays the same. The only thing that will differ is your x becomes y and y becomes x. Or in other words, we can say is x here is the dependent variable, y is the independent variable. So independent becomes dependent and dependent becomes independent. That means x would come here, y would go out. Let's take up another example. Let's say we have y equal to 3 to the power x, and when we have to change it to the inverse, or when we have to change it to the logarithmic function, we would write it as log to the base of 3. So base here is 3, base stays the same. We just have to interchange x and y, and it looks like this. So if we have y is equal to 3 to the power 5, we write it as log to the base of 3 of y equal to 5. Let's take up another example. So if we have 3 equal to 2 to the power x, and we want to change it to logarithmic form, we have to do log to the base of 2, because the base is 2. We have to interchange this 3 and x. Here x is the power on 2 and 3 is outside or on the other side of the equal to sign. In this case, x will go on the other side of the equal to sign and 3 would come along with the equation. So always remember, the base stays the same. The number that's outside comes with the log, and the number that is inside the exponential equation as a power goes outside the log. We can do vice versa as well. So if we are given log to the base of 4 of x equal to 8, and we have to change it to exponential function form, base is 4, so we would write on the base first, to the power of 8 is equal to x. So the base of log and the base of exponential function does not change. The only thing that changes is these dependent and independent variables. Here 8 is independent, x is dependent. Here x becomes independent and 8 becomes dependent. Here we learned how to change logarithmic functions to exponential, or exponential functions to logarithmic functions. Now we would further differentiate between exponential and logarithmic functions, and we'll take the original example to do so. The first example of exponential function was y equal to 2 to the power x, and when we changed it to the inverse function of the logarithmic function, we had log to the base of 2 of x is equal to y. The reason we are writing x here and y here is that x is considered to be independent always and y is considered to be dependent. But remember, these are actually the inverse values of these. So if these are the parent function equations, how would the transformed function equation look like? Let's put the transformed function with this small prime sign. So y transformed would have a in front of this whole function, 2 to the power, because x is raised as a power, so k and d would also raise to the power of it, and plus c. Here the transformed function would look like a log to the base of 2, with x goes k, x minus d plus c. So whatever happens to x, the same thing happens to k and d, because x comes with the logarithm of base 2, k and d will also come with the logarithm of base 2. A is multiplied with the whole function, so that comes outside, and c is usually added or subtracted, so that goes outside on the right side with a plus or a minus sign, but your general equation should have a plus sign. Now these are certain things that we have to keep in mind when we are drawing the graphs of the exponential and the logarithmic function. In exponential functions, we would see horizontal asymptote, and the horizontal asymptote is defined by y equal to c value, whereas in logarithmic functions, we would see vertical asymptote, and that is defined by x equal to d. So everything is inverted in logarithmic function because logarithms are inverse of exponential functions. Here we have horizontal asymptote, here we would have vertical asymptote. Here it's y equal to c value, here it's x equal to d value. We would have a y-intercept in exponential functions, and the value of y-intercept is 1. We would have an x-intercept in logarithmic functions, and the value of x-intercept is 1. Domain of exponential functions is xer, and range is equal to yer, where y is going to be greater than 0. That is your horizontal asymptote. In logarithmic function, domain is xer, where x is going to be greater than 0. This is with respect to this parent function because d is 0 in this case. If d is not 0, then here goes that number d. Here also, because c is not there, so c is 0. That's why range here would have y greater than 0. Range in this case would be yer. Now let's turn these functions into graphs. So this was y equal to 2 to the power x, and this was y equal to log to the base of 2 of x. Before turning it into graphs, let's turn it into table of values. So this is x, this is y. X, the easiest x values that we can pick for exponential function is -1, 0, and 1. When we put 2 to the power of -1, we get 1 over 2. So y value is 1 over 2. When we put 2 to the power of 0, we get 1. When we put 2 to the power 1, we get a 2. Now, if we write on table of values for logarithmic function, we just flip y and x values because inverse functions, y and x is flipped. So here x would be 1 by 2, 1 and 2, and y would be -1, 0, and 1. So in this case, we are drawing the table of values from its counter exponential function, but we do not have to do that always. Just remember, whatever is the base, you reciprocate the base and take it as the first x value. Then the next x value is 1, and then the next x value is the base itself. When you reciprocate the base, your y value will always be -1. When your x is 1, your y value will be 0. When your x is the base itself, your y value will be 1. You can find this out by putting this in the calculator. So log to the base of 2 of half will give you a -1. Log to the base of 2 of 1 will give you a 0, and log to the base of 2 will always give you a 1. Just for the sake of understanding, let's take up another example, but we would not be drawing this. We would only be drawing the pink one. We have y equal to log to the base of 3x. When we turn this into table of values, x, the first x would be 1 over 3, next x would be 1, next x will be base itself, that is 3. Y value will be -1 when we reciprocate the base. Y value will be 0 when we leave the x value as 1. And when we leave the x value as the base itself, y value is going to give you a 1 answer. So y's never change in logarithmic functions if you take these x values. And how do we decide it? If we write it as a general log to the base b of x equation, then we always remember this would look something like this. 1 over b gives you a -1, 1 would give you a 0, and b itself will give you a 1. Coming back to making these pink graphs, so we would make the axes. We know for exponential functions we have horizontal asymptote at x equal to 0 because the c value, we know the horizontal asymptote is y equal to 0 because c value is 0, and that's for exponential functions, so we would make our horizontal asymptote. And for logarithmic functions we have vertical asymptote at y equal to 0, so we would plot the asymptotes first. Once we know the asymptotes, all we have to do is just plot these points. When x is -1, y value is half, so let's keep y as 2 here, 1 here, so half will be somewhat here. When x is 0, y is 1. When x is 1, y is 2. When we connect these points, this is how the graph looks like, and this is y equal to 2 to the power x. That's the exponential function graph, and the base is 2. Here x value is, let's say we put in -1, 0, 1. We need the x value up till 2, so we'll extend the axes. And here we would see x value as 2. So the first x value is half, that would be here. When x is half, y is -1, and -1 is going to be here. When x is 1, y is 0. When x is 2, y is 1. And when we connect these points, we would get the graph like this. It will not cross the axes because here is the vertical asymptote. It would just go close to the vertical asymptote. And we would notice here that we have x-intercept at x equal to 1. We have y-intercept at y equal to 1. Domain is XER because it goes from negative infinity to positive infinity. Range is YER where y value is going to be greater than 0, and the 0 is nothing but the C value. Here domain is XER where x has to be greater than 0 because this x value cannot, or this graph cannot trespass this vertical asymptote. So it will always stay on the positive x side. And range is YER because it's going all the way from negative infinity to positive infinity. So we would notice here one thing, that here the base is 2 and here also the base is 2. So in this example, what we covered up was when the base value is greater than 1. We can also have base value that lies in between 0 and 1. And in that scenario, how do we differentiate between the functions is? So we have exponential function as y equal to, let's say, 1 by 2 to the power x, and here log to the base of 1 by 2 of x would be equal to y. Its transform function would look like, or transformed equation would look like, a half to the power of k x minus t plus c, and here the transformed equation would look like a log to the base of half k x minus t plus c. Rest of the things stay the same. We would have a horizontal asymptote of y equal to c. We would have a vertical asymptote of x equal to d. We would have a y-intercept of 1. Here also we would have an x-intercept of 1. These things stay the same. The only difference is that the base value is now in between 0 and 1, and the example that we are taking is when base is half. Here also we are taking base is half. Next, if we want to turn this into a table, we have y equal to half to the power of x, and we have y equal to log to the base of half of x. When we turn this into a table, we would get x and y values as, in exponential function, x values are always negative 1, 0 and 1. These are the simplest x values. And the corresponding y values will be, when we put in half to the power of negative 1, because the x is negative 1, we get 2, so we would get 2 here. When we put this to the power of 0, we would get a 1, and here we would get a 2. Here, when we interchange x and y, or we use that general form equation, where the first value is the reciprocal of the base. Base is 1 over 2, so reciprocal of base is 2. The next x value is 1, and the next x value is the base itself. Y values are always negative 1, 0, and 1. Let's use this to make graphs. So this is our axes in both cases. The horizontal asymptote here is going to be y equal to c, and that is 0 because c is 0 in this case. If c is any other number, then this horizontal asymptote would move up and down accordingly. X values are negative 1, 0, and 1. When x is negative 1, y is 2. When x is 0, y is 1. When x is 1, y is half. When we connect all these points, we would be able to get this kind of a graph. Similarly, here we would have a vertical asymptote, and d value is 0 in this case. As the d value is 0, so the vertical asymptote will be 0. The x values that we have here is 2, 1, and 1 over 2. So we would use 1, 2. 1 over 2 is half, that would be here. When x value is 2, y is negative 1, so that point would be somewhere here. When x value is 1, y is 0, that would be here. When x value is half, y is going to be 1, that would be here. When we connect all these points, we would be able to get the graph, and the graph would look something like this. Domain here would be XER, and why so? Because again, our graph goes from negative infinity to positive infinity. Range here is YER, where your y value is always greater than 0. In this case, domain is XER, but it has a limit because it will never be negative, so x would be greater than 0. Range is YER, and that's it. No limits, because from negative infinity to positive infinity, we would see the graph going all the way. Now, one thing we would notice here is, like, how is this different from the pink graphs that we drew before? is that when the base function is a reciprocal, or when the base function lies in between 0 and 1, we would notice that the graphs are decreasing graphs. No matter it's an exponential or a logarithmic function graph, the graphs are decreasing all the way from negative infinity to positive infinity. Here also the graph is decreasing. And when we go to these graphs are increasing all the way from negative infinity to positive infinity. Here also all the way from the vertical asymptote to positive infinity, the graph is going up, up, up. So it's increasing graph. Therefore, the only difference between both the graphs is when b is greater than 1, we would see increasing graphs, and when b value lies in between 0 and 1, we would see decreasing graphs. But all of the properties of graphs, or all of the characteristics of graphs, would stay the same.